Hello again. Let's talk about heat transfer again, but this time heat transfer by electromagnetic waves. So we'll talk more about electromagnetic waves in the second semester, but these are waves of electric and magnetic fields. So again, you'll learn what those mean in the next semester, but for the moment, let's just say you know what a wave is, and so these waves are made up of these things called electric and magnetic fields, and these waves have something called a wavelength, which is the distance from one peak of the wave to the next peak of the wave. And the wave of this type that you're most familiar with is probably light. Light is a type of EM wave, electromagnetic wave, and it has a wavelength, lambda, from 400 nanometers to 700 nanometers is the spectrum, we say, of all of light waves. So waves of this type of electric and magnetic fields that have wavelengths between 400 and 700 nanometers, we detect as humans as visible light. The 400 N being the violet end up through the 700 being the red end of the spectrum. But there are other wavelengths as well. There are wavelengths longer than 700 nanometers. If they're a little longer, it's the infrared part of the spectrum, or just the IR. And wavelengths that are longer than that still are microwaves. And beyond that, radio waves. Microwaves like you cook your food with. To shorter wavelengths, as you go this way, a little bit shorter than, say, 400 nanometers, is ultraviolet light, or just UV you might call it. Shorter still is a region called X-rays. So just like when you have your bone X-ray to see if you've broken it or just bruised it. And shorter still is something called gamma rays that are emitted in, say, nuclear reactions or nuclear explosions. So this is the electromagnetic spectrum, we call it. These are the electromagnetic waves. So what we're talking about today is when these waves transfer energy from one location to another. And for our purposes at the moment, we're mostly talking about this region of the spectrum, when heat is being transferred by visible, infrared, or ultraviolet light. That's what mostly comes from the sun and from hot objects. And for hot objects on Earth, it's mostly infrared radiation. That's the radiation when you just feel heat from an infrared lamp. That's these wavelengths of light. So heat transfer by these waves, or heat transfer by electromagnetic waves. So what we want to be able to do is like we did for conduction and convection, we want to be able to compute the power transfer. Now deriving the power transfer for these waves is actually very complicated. So I'm only going to be able to tell you the result. If I have some object, and that object has some surface area, A, and that surface area would be the sum of all of its areas. So it'd be like this area plus that area plus that area, or if it's a sphere, it'd be the 4 pi r squared of a sphere. If it's just a flat disk, it'd be the area of a disk, whatever surface area it has. And if it has some temperature TO, T of the object, and if it's embedded in some environment, and the environment has a T E of the environment, then the power transfer, P, that's still Q over T, rate of energy transferred, looks like a number sigma times epsilon times that area times T of the object to the 4th power minus T of the environment to the 4th power. That 4th power is huge. The fact that as the temperature goes up, the amount of energy being emitted per unit time, the power goes up as the fourth power is huge. So if you double the temperature, the absolute temperature, it's got to be in Kelvin. So if you double the temperature, say from 300 Kelvin to 600 Kelvin, that means this goes up by a factor of 2 to the fourth. That means you get 16 times the power emission. So this is the temperature in kelvins. This is the surface area, because that's the place where the energy can be emitted from, the surface. The energy from the sun, for example, comes from the surface of the sun. It may be produced deep in the interior, but we only get the energy from the surface. This is something called the emissivity. And it depends on just how good the object is at emitting. So black objects are very good, for example, so a good emitter would have an emissivity of approximately 1, but a shiny object is a very poor emitter, would have an epsilon approaching 0. So emissivities are numbers between 0 and 1 that just say how good of an emitter is this. Also, good emitters are also good absorbers. So something's good at emitting radiation, it's also good at absorbing radiation. And then this is something that's a constant of nature. It's called the Stefan-Boltzmann constant. And it's an interesting value. Sigma is 5.67 times 10 to the minus 8 watts per, make sure I get the units right, meter squared Kelvin to the fourth. That's not an 8. Yeah, it is. Let's see. 5.67 times 10 minus 8. Right. So 5, 6, 7, 8. I would give you that number on a quiz, but I think it's easier thinking that's 5, 6, 7, 8. So that's called the Stefan-Boltzmann constant. And so this, again, this is very hard to derive, but it is the equation that tells you power transfer. So let me do an example for you, and then of course we'll practice it in class. So what I'm going to do is I'm going to do an example of power transfer from a cube, like I have drawn here, and I'm going to let it be a ceramic cube. And I'm going to let the ceramic cube be at T equal 373 degrees Celsius. This is 646 degrees Kelvin. Actually, we don't use the degree symbol with Kelvin, so 646 Kelvin. For ceramic, we're going to let the emissivity be approximately 0.7. We're going to let the environment be at a temperature of 20 degrees Celsius, so 293 Kelvin. 273 plus 20 is 293. We're going to let the cube have 3.5 centimeter sides, so 3.5 by 3.5 by 3.5. And we're going to say if this cube is at 646 Kelvin, cube of ceramic, what's the power being emitted into the environment? So we know sigma, we know epsilon, we know the temperatures, we just need the area of the cube. So area is 0.035 meters cubed. It's the area of a cube. No, it's not. That's the volume of the cube. That's wrong. It is 6, because it has 6 faces. 1, 2, 3, 4, 5, 6 times 0.035 meters squared. So each face is 0.035 meters by 0.035 meters. That's the area of one face. And there are 6 faces, just like on a die. And that is 0.0074 square meters. So I want to check that, make sure I did that right. 0.035 g squared 6 times. Yep. It's actually 0.00735, but I'll use 0.074. So now the power is sigma is this 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. Epsilon has no units, it's 0.7. Area is 0.0074 meters squared. The object's temperature is 646 Kelvin raised to the fourth power, so be sure you know how to do that in your calculator. Minus 293 Kelvin raised to the fourth power. And when you do all that, you get a nice simple 49 watts of power this object is emitting into its environment. So there you have it. And that was the only topic I was going to cover for the day. So I'll see you soon.